This section examines the Electronic Control Unit, or ECU. The ECU is a microcomputer. It's constructed from printed circuitry and contains a large number of electrical components, including many semiconductor devices. Its input devices receive data as electrical signals. They come from sensors and components at various locations around the engine. Its processing unit compares incoming data with data stored in a memory unit. The memory unit contains basic data about how the engine is to operate, and an output device pulses the electrical circuit of the solenoid-type injection valves. It is normally located in a safe place behind a kick panel in the footwell, under the passenger seat or in the boot, and connected by a multi-plug or plugs to the vehicle's wiring harness. The core function of a basic ECU in an EFI system is to control the pulse width of the injector. More sophisticated models also control other functions, such as idle speed, ignition timing, and the fuel pump. These wider systems are called engine management systems. The more precise control they allow is very effective in reducing fuel consumption and exhaust emissions. The ECU adjusts quickly to changing conditions by using what are called programmed characteristic maps, stored in the memory unit. They are programmed into the ECU just as data is programmed into a computer. Characteristics means the engine's operating conditions, and they are called maps because they map all of the operating conditions for the engine. They're constructed first from dynamometer tests, then fine-tuned to optimize the operating conditions. This data is stored electronically. Ignition timing is crucial in this process. Between one spark and the next, the ECU uses data it receives on engine load and speed to determine when the next ignition point will occur. It can also correct the map value using extra information such as engine coolant temperature, intake air temperature, or throttle position. Putting all of this together, it arrives at the best ignition point for that operating condition.
The throttle position switch signals a closed throttle setting to the ECU. It compares this with data in its memory about how the engine is to operate and determines a setting to suit this data. Its output pulses the electrical circuit of the injectors. In this case, the pulse width ensures a smooth and stable engine idle. The throttle position sensor signals a rich mixture requirement to the ECU. It compares this with data in its memory about how the engine is to operate and determines a setting to suit this data. Its output pulses the electrical circuit of the injectors. In this case, it increases the pulse width of the injector. The coolant temperature sensor signals cold engine to the ECU. It compares this with data in its memory about how the engine is to operate and determines a setting to suit this data. Its output pulses the electrical circuit of the injectors. In this case, it increases the pulse width of the injector. The coolant temperature sensor signals hot engine to the ECU. It compares this with data in its memory about how the engine is to operate and determines a setting to suit this data. Its output pulses the electrical circuit of the injectors. In this case, it decreases the pulse width of the injector.
Settings are made for various operating conditions according to fuel consumption, engine torque, exhaust emissions, knocking tendency, and drivability. That means, for example, that starting ability can be improved by making timing during cranking depend on cranking speed. Timing at low idle speeds can be set for low emissions, smoothness and fuel economy. For part load operation, the emphasis is on economy and drivability. At full load, it is set for maximum torque without detonation. Using the digitally stored map, the ignition point is set for each operating condition, without affecting the settings for any other condition. All of this raises an engine's overall efficiency for all operating conditions. Corrections to ignition timing, combined with those to the injector opening time, provide the optimum values to achieve the best combustion. With higher compression ratios, there is more risk of detonation and damage to the combustion chamber. A knock sensor allows ignition timing to be calibrated to achieve the best setting for normal operating conditions. Knock or detonation can then be eliminated separately using closed-loop knock control. When a detonation signal is received, the control unit retards the ignition setting to bring detonation under control. A turbocharged engine is different. Simply retarding the ignition could increase the already high temperatures at the exhaust-driven turbine. But reducing the boost pressure at the same time brings detonation under control quickly. As soon as knocking is detected, ignition is retarded, which works immediately. Reducing boost takes longer, but as soon as it takes effect, the control unit returns ignition timing to its optimum value. The control unit can also control other output functions, such as engine speed limiting. When actual engine speed reaches a programmed maximum, the fuel injection pulses can be suppressed. This protects the engine from over-revving without disadvantaging its operation. The ECU can control the fuel pump. For safety reasons, when the ignition is turned on and the engine is stationary, the fuel pump operates for a few seconds only, enough to prime the engine for starting. It starts again during cranking and when the engine is running above a specified minimum number of revolutions per minute. Some exhaust gas is allowed to recirculate to control the nitrogen oxides. How much exhaust gas does this can be controlled by vacuum and vent solenoids in the vacuum circuit of the EGR valve. When loads are put on the engine, such as from air conditioning or lights, the control unit regulates how much the idle speed control valve opens to maintain a preset idling speed. Fuel vapours stored on the active material in the canister are drawn into the cylinders and burned when engine operating conditions allow. At different engine speeds and loads, the control unit operates solenoid valves that alter the effective pipe length of the manifold. This extends the torque output over a wider range of engine speeds. The cooling fan is switched on automatically when the air conditioning is switched on. Instantaneous fuel consumption can be displayed on the instrument panel in front of the driver. The check engine lamp is a warning light on the instrument panel. It is lit up by the control unit to warn of malfunction in engine management. The check engine lamp can also indicate fault codes. They can be a series of lamp blinks or voltage pulses from the control unit. They give a number for the kind of fault that is occurring. One lamp blink, followed by a pause, then 3 blinks in rapid succession, indicates code 13, which may mean, for that application, that the oxygen sensor voltage is not changing, leaving the engine in open-loop operation. When the control unit does not receive a signal from a component, it uses a substitute value from its memory bank. The engine may still operate near its normal level, and the driver may not realize a problem has occurred. In some cases, if the fault is in a major component, the control unit may go to a limp home mode, with a fixed injection duration and ignition setting. The vehicle remains drivable but with reduced performance, allowing it to be driven to a convenient service point. With a data scanning tool, an engine management function can be viewed. All of these functions together are a snapshot of the state of all inputs and outputs at that instant. This data can then be analysed. A control unit can use data from its memory to adjust engine settings over time. This is called adaptive learning. It only occurs with feedback or closed-loop operation. This vehicle is using medium throttle with light loading and mild acceleration. Its control unit will set fuel delivery for a specified pulse width. However, if fuel pressure is less than when the vehicle was new, feedback from the oxygen sensor can cause the lambda control to increase injection time. The control unit learns the new time and stores it in its memory for future use in that condition. If the battery is disconnected or memory is lost, the settings revert to the manufacturer's program specifications. And the vehicle then has to be driven in a range of conditions to let the control unit, in effect, relearn the engine's fuel settings. This section examines cold start systems. When a cold engine starts, some of the fuel injected by the main injectors condenses on the cold intake port or the cylinder walls. Less fuel stays mixed with the air, which weakens the mixture. To overcome this and ensure a rapid start, an extra supply of fuel must be provided. In some cases, during engine cranking, extra injection pulses in each revolution can provide the extra fuel. It depends on engine temperature, and there is a time limit to prevent flooding. The cranking period is followed by an after-start enrichment. Over about 30 seconds, this slowly reduces to normal warm-up. The engine then responds steadily immediately after releasing the starter. More air comes from an auxiliary air valve or bypass air control valve. This bypasses the throttle valve to raise the engine's idle speed when it is cold and during warm-up. Extra fuel can also come from a separate cold start injector normally mounted centrally on the plenum chamber. It's supplied with fuel under pressure from the fuel rail and only operates when the engine is cranking. A switch called a thermo-time switch immersed in engine coolant completes the electrical circuit. It controls the operation according to engine temperature. This ensures the injector operates under cranking conditions only when the engine is actually cold. The control unit can help cold starting and provide cranking enrichment by increasing the pulse width of the injectors. This is in addition to the cold start injector operation and is again temperature controlled. Some sequential systems use a pre-injection of fuel. This means all injectors open simultaneously to provide an initial injection of fuel. This happens only during cold cranking, and there is a time delay to prevent pre-injection occurring again within a certain time if the engine does not start. The system reverts to sequential injection when the engine starts. Alternatively, simultaneous injection may be used during cranking and also in the warm-up period. Once a preset temperature is reached, the control unit changes to sequential mode. This section examines idle speed control systems. Base engine idle speed may be set by adjusting a screw on the throttle body. This sets how much air flows through a bypass passage from the intake air side to the manifold side of the throttle body. However, if more load is put on the engine during idle, its idle speed may fall to a level where the engine stalls. Higher load can be caused by extra frictional resistance that occurs in a cold engine and by electrical loads from headlights or the cooling fan. Shifting an automatic transmission into a drive range or engaging the air conditioner compressor clutch will also cause a drop in the idle speed. The extra air needed for a cold engine can come from an auxiliary air device. This one has a connecting hose from the intake air side to its controlling passageway and a return hose to the plenum chamber. It bypasses the throttle plate when it's in operation to provide the extra air. The control unit reacts to this additional air by metering additional fuel. This makes more air-fuel mixture available during the warm-up period. How much air bypasses the throttle plate can be controlled automatically by the ECU. It receives data on idle speed and idle conditions and uses it to provide an output to a solenoid-operated taper valve or to a stepper motor pintle. The valve varies the opening of the bypass passageway and changes the idle speed to suit. The position of the throttle plate can control idle speed automatically. A DC motor works a plunger in contact with a lever attached to the throttle spindle. As idle conditions change, the control unit can extend or retract the plunger, which increases or decreases the throttle plate opening. This provides the desired idle speed. If the control unit is programmed to maintain a fine control of the idling speed, perhaps to within 100 RPM, ignition timing can be used. Advancing the ignition point increases engine speed, just as retarding it decreases it. Hall effect sensors can also provide a voltage signal and, like the inductive type, can be mounted on the crankcase wall or inside the housing of the distributor. The sensor has a permanent magnet and a Hall switch as part of its assembly and an air gap between the magnet's north and south poles. The switch is on one pole of the magnet and an interrupter ring with a number of square-shaped blades or segments rotates through the gap formed by the poles. When it's used in a distributor, this interrupter ring has the same number of blades as engine cylinders and a corresponding number of windows or gaps between the blades. The magnetic field is strongest when the gap is aligned with the poles. This allows the switch to earth a low current signal voltage that is applied to it. When the interrupter ring rotates so that a blade is in line with the poles, the magnetic field is shielded and the signal voltage is not earthed. With continuous rotation, the blades repeatedly move in and out of the air gap, and the signal voltage will appear to turn on and off repeatedly. The control unit uses this on-off signal to detect engine RPM and to control ignition timing. If a sequential injection mode is used, the position of the camshaft must also be signaled to the control unit. This is done by making one blade of the interrupter ring shorter than the others. It's called a signature blade. It passes through the sensor and alters the signal so that injection commences at the correct time in the cycle. Since the distributor rotates at camshaft speed, the sensor in the distributor provides camshaft position readily. When the sensors are on the crankshaft, a separate sensor is needed for camshaft position. It identifies when to commence injection for the number 1 cylinder. Injection for the other cylinders then occurs in the same sequence as the firing order. Crank angle position and engine RPM can be detected optically. A signal rotor plate is attached to the distributor shaft. It has 360 slits at 1 degree intervals on its outer edge. Inboard of the 1 degree slits are 4 slits, one for each cylinder. They provide the reference points for the ignition timing and the fuel injection. One is larger than the others to provide the signature effect for the number 1 cylinder. As the rotor plate turns, it passes between 2 sets of diodes, positioned in line with the slits. The diodes above the rotor plate are light-emitting diodes, while the ones below are photodiodes. When provided with a suitable voltage, light-emitting diodes transmit a fine beam of light. Photodiodes receive this light and use it to make a voltage output signal. When a slit is in alignment, the light beam passes through and a signal is transmitted to the control unit. When the slit is out of alignment, the light beam is interrupted and the signal falls to 0. The control unit uses the interruption of the light beam and the 1 degree slits to gauge engine RPM. It uses the interruption of the light beam and the signature slit to gauge the position of the number 1 piston. All of this data is used to keep close control of ignition timing and fuel injection. This section examines modes of fuel injection for petrol engines. A mode of injection describes the timing and the sequence of injecting fuel. Simultaneous injection means every injector opens at the same time. Fuel sprays into each intake port where it stays until the inlet valve opens. During each engine cycle, the injectors open twice, and each time they deliver half the fuel needs of each cylinder. This happens regardless of the position of the intake valve. The injectors are triggered by the ignition system. So for a 6-cylinder engine, the control unit triggers the injectors on every 3rd ignition pulse. Sequential injection means injection for each cylinder occurs once per engine cycle. It is timed to each individual cylinder in the firing order. Fuel spray stays in the intake port until the inlet valve opens. Grouped injection divides the injectors into 2 groups. A 6-cylinder engine can have injectors 1, 2 and 3 in Group 1 and injectors 4, 5 and 6 in Group 2. The control unit operates the groups in turn to spray fuel once per engine cycle. Group 1 injects, then 360 degrees or 1 crankshaft rotation later, so does Group 2. This happens regardless of the position of the intake valve. Just 1 injection provides the full quantity of fuel for each cylinder during that engine cycle. In some applications, different modes of injection are combined, so that the mode changes according to the operating conditions. Sequential mode may be used for low engine speeds, changing to simultaneous mode at high speeds. The same principle is used in changing from light loads to heavy loads. Similarly, the mode may change from group injection to simultaneous. Using different modes for different operating conditions makes the most of how the fuel is used, and that improves power output, fuel economy, and emission control. This section examines variable intake manifold systems. The air intake manifold for an EFI multi-point engine normally has long branches of equal length. The long branches increase the pulsing effect of the airflow in each pipe and help charge the cylinders. The more air drawn into the cylinder, the denser is the air-fuel mixture when the inlet valve closes. and it's this density of the air-fuel mixture that determines how much pressure develops in the cylinder during combustion, and the level of thrust on the piston to turn the crankshaft. The characteristic torque curve of a naturally aspirated engine depends mainly on how the engine's mean pressure changes across the RPM band. The design of the inlet system largely determines the mass of air that can be drawn into a cylinder at a given engine speed. So that means the inlet system largely determines the engine's torque curve. In general, a long intake manifold produces high torque at lower engine RPM, and higher torque is obtained at higher engine RPM with a shorter intake manifold. Manifolds that respond to changes in engine load and speed by changing their effective length are called variable inertia or intake charging systems. They can have controlling valves operated by the engine management system, which can extend the primary type manifold into 2 or 3 stages. The primary section is made long and narrow for the low range of RPM. The secondary section is shorter and wider for the high range of RPM. This combination maintains a high-speed airflow in the system. The 3-stage manifold extends the torque curve so that the torque curves overlap each other as advantageously as possible.